if you remember, we were kind of putting this together. Let me turn down the lights in here so you can actually see the projector. There we go. So I was putting together really basic kind of notes on my findings and everything here. And what we ended up getting to was a point where we were looking at these two strings, which are the ones with all the X's and the Y's in them. And I was talking through why it is that, here's the dump. So this is basically picking up exactly from last session. Why it is that they're showing up here in front of the URL. And if you recall, one of the observations I had made earlier on when I've looked through this before is that this is put here as kind of a marker so that if someone wanted to go and change the code after the fact, as long as they include this marker in front of whatever text they put in there, that will allow them to tell the program where in the file this URL, this location to go and get commands from is located. Another hint that I didn't quite point out last lecture that also kind of leads us down that path is that if I go down here, I'll see that those markers, those combinations of characters actually happen again later on in the file, but they happen without anything following them, meaning that again, relying upon the expectation that all of the data that's present in this file has some sort of function to it. We're going to draw the conclusion that anything that's in this file has some sort of functional purpose. Very common that if it didn't, it might have been stripped out during link time, or it just wouldn't show up in the file at all. Of course, it's not always a safe assumption, but as a good kind of starting out point, in the absence of any other evidence to the contrary, it's definitely a good assumption to conclude that every single piece of data that you see here has some sort of purpose. Looking through that, I made a note of it over here. Now comes the harder part, which is how do we either kind of confirm that hypothesis that these things are trying to tell us are trying to tell the malware what the URL it is that it wants to pull commands from are, or possibly if they aren't that, how do we determine what their purpose is? Likewise, we also documented a large number of commands here too. And then there was one other thing that I really glossed over, but I'll show it to you anyways, just for your information. It was also this. So this ends up being a long string of characters. If you were to count the number of characters here, and I can do it right now, it's 64 characters long. You'll notice that every single character in that string happens exactly once. Typically what you'll find is a sequence of characters like this is also reflective of a lookup table for base 64 conversion routine. So if you're familiar with base 64, and I can definitely bring it up here for you. It's really common in coding. It's used in email, among other things. And the best thing about it is that there's a mapping that allows you to take binary data and then fit it into something that's the alphabet, or that's an alphabet made up of characters you can type on your keyboard. So this ends up being very useful for anybody trying to transmit binary data over, say, a medium that may not support all binary byte values. So what I will say is, again, when you're looking through here, every single one of these things has some sort of functionality to it. So for instance, if you see something like this that says like ready, exclamation point, that has some sort of use. Obviously, it was intended for a person to see it. My assumption would be that it's not intended for the target, the person who was being attacked, to see. Instead, it's trying to tell the attacker, for instance, that something is ready, something is available. Or at least that would be my conclusion initially. So if I want to look into it, I can look into it with a code analysis tool. It will take a lot of time to go through every single string in here, and I definitely don't recommend having to do it, except in, at least, especially not in class, and I won't necessarily have you dive into trying to do the code analysis on every single one of these in any sample. But following the steps that we went through in the last class, kind of using your head to draw conclusions about what something likely might be, what might be the purpose of something. It's definitely part of the game, something I will expect, and then later on, what we're about to do now, using some of the code analysis tools to try and confirm or deny one's hypothesis about something, or maybe just get more information to build a better hypothesis. So I already started analyzing these, and I've actually got 3 of them, so I put some notes together for them. This one, obviously, is the one that we went through, so I had a lot of information that I was able to gather from the analysis we've already done. The other 2, we'll put together some more if we have time. And I'm going to start with this one, and I put some notes just to give us some jump ahead so that I don't have to go fumbling around in the user interface in the middle of class. But I'm going to load up Yara Pro. So here, it's loading up. So as you can see, I already opened these up in Yara Pro. What I'm going to actually do, usually you're presented with this window here with nothing in here when you load up Yara Pro. I'm actually going to say new, which means new project. So it means I want to open up a new file to analyze. Generally, they offer a whole bunch of different types of files. You can see that if I have Linux malware or Unix malware, I can analyze that. If I have malware for Mac OS X, I can also look at that. I can look at some Java code, I guess, with it. .NET, other sort of files, things like that. So this one's kind of fun. Nintendo 64 ROM image. Might be a fun one to look at some point in Game Boy. So as you can see, there's a lot of different file formats that are supported here. The primary ones, again, that you're going to run into are going to be these 2, because these are the predominant packaging for Windows programs. And the reason why you'll see them be the predominant carrier for malware is because the majority of people out on the internet run Windows servers, have Windows machines, use Windows in their daily life, and the attacker would like anything they deliver to the users to behave like a normal Windows program. So in order to behave like a normal Windows program, it has to be built out of the same tools that a normal Windows program will be built out of. It's not always the case, and it's changing as time goes on, because we are seeing a lot more Macintosh systems that are getting adopted by people. Linux is becoming more popular, especially in the server space. So I do foresee in the future that we'll see expansion in those areas. But for now, as it stands today, and as it will probably stand when all of you graduate, Windows malware is going to be the predominant thing. The other thing, too, I'll say is that all the techniques that I'm going to talk about here are going to apply across, are going to transfer across the board. The only difference is that libraries change, the functions that are available from the operating system and from the standard runtime, those things change. But the concepts stay the same. Like, for instance, if you recall, we were looking through, we were using objdump at one point to look through a Linux program and also looking through a Windows program. And both of them had roughly the same construction, just the structures were different. But they had the same concept behind them, which is both of them are built out of segments or sections. and those sections contain specific types of data in them, and there's a bunch of fields that tell what kind of data is in there. So you're going to deal with that stuff regardless of the environment that you're working on. So these that we collected happen to be an exe file. So I'm going to go ahead and open it up. And the reason I'm opening this up new is you get to see the analysis phases that this goes through. So I'm going to overwrite my old database with a brand new one. What I typically do is I set this option on, which allows it to attempt to extrapolate information about the DLLs that are going to be used by the program, and then also create resources segment, which means that if you recall when we were going through with objdump and I showed the sections of the file, there was some code sections and there were some data sections, and one of those was the resources section. And when I looked into it in front of you, there was some string data in there, and there's I talked about how the icon that the program uses is also stored in there, and a number of other things like the version info and things like that. Dialog boxes, for instance, are also stored in there. Because that section can get really big sometimes, and it's not always necessary, they actually don't load it by default. So you have to opt into loading it. So now what it's going to do is what you're seeing it do right now is it's walking from the beginning of the file all the way down to the end of the file, and it's trying to find all the different code blocks. So if you remember that tiny program I put together where we compiled it as a C program, I'll actually jump back to it for a moment. I believe it was this one, this ASM program. So when I was showing it to you, this is the one that's in that slide deck where I broke it up into the control flow graph for you. So I was able to do that by looking at the disassembly, and then I mapped that back to the source code. So all those comments that are in the source code are comments I put in there after I analyzed this. Whoops. After I analyzed this to get the different these things, the different labels that were there, the different jump points. So what's happened here is that IDA Pro has gone through and done that programmatically for us. And it's broken it up into a bunch of graphs. The way that IDA Pro works, and I'm going to expand this because my screen real estate is very limited here. That came out decent on the screen. The way IDA Pro works is it goes through the system and it tries to see if it can identify functions that are either in the, I believe that, yeah. Sorry. There we go. So this allows us to go back to different spots. So I can show you this on the names. So this is the list of all the functions that were found in the program. And so it's got like an I here for some of these, which means that they're actually imported, I believe, from a different, this is under the names section. So these ones that are I are ones that are those imports. So if you remember when we were looking through the objdump output, it showed a DLL file, and then underneath it showed a list of the symbols that were imported from that. All those symbols are names, and they can point to functions, or they can point to variables or anything like that. So you're seeing, what you're seeing right here is IDA Pro actually going through and enumerating all of those things and putting them in a list for you. It also attempts to find all the functions that are stored within the file. So in some cases, a program may be statically linked with some runtime code that came with Visual Studio. And that's what you're seeing here. So for instance, there's this inet n2a function or whatever. I think it's over here. Oh, so this one's another import definition. So go, yeah, names. Here we go. Yeah, so it's got some functions here that maybe, nope. Yes, all these are just library functions that are brought in. Sometimes it thinks they're functions, sometimes it actually properly recognizes them as imports. But the idea here is you can go through it, and you should actually be able to, we'll start with the main function, which is up here actually. You should actually be able to walk the program structure to try and figure out what it's doing. So for instance, here's the main function. You can see there's a lot of code in here. This is the code that would normally be what is executed when the program starts up from the command line or from being run from a document. So this would be what you'd call the entry point for the program. And we can verify this if we go here. So I'm going to go back to there we go. So I'm going to show the headers for the ex1 file. And let me see if I can remember what right here, address of entry point. Okay, it's got this. So I'd have to do the math in my head, but well, I may not have to. Let me go back here a second. So it's the address of the entry point is 3712, and then image base is going to be this, so it'll probably be 403712. So yeah, so right here, 403712, which is the address right there in that column. That's the entry point. So that's where it actually starts. Typically, what happens in a Windows program is it will run the start function out of here, and then that ends up doing a bunch of setup code that ends up getting you to that main function that we actually put in the C code. So you see a lot of that. When I'm running, whoops, I meant this one. When I'm running this objdump tool to look at the program headers, I'm trying to figure out where this program is supposed to start executing code. Typically, what it ends up being is this number, which is telling it where in memory it wants it to load the program. So the program itself just sits in a compact file on disk. When you run the program, you load it into memory, and you put all those sections into different space in memory. And that, again, if I go down here, the table's right here, right? So this tells you where in memory each one of these sections are supposed to be found. This tells where it wants, like, the beginning of the program to be loaded. So that ends up being for 400,000 hex. What I ended up doing was looking for the code that was located at this plus this, because it's a this right here is a offset from the beginning of the actual file memory or program memory, and then this ends up being a where in memory the 0 byte, you know, the entry byte for that program, or the first byte for that program is going to be loaded. So better way to put it is, if you remember that MZ is the first 2 bytes within the file, the M in this program is going to show up at that location in memory, and then the rest of the file is going to follow after that. So the other thing that I'll add is that it attempts to determine what the different functions are based upon the names that are embedded in the program. A lot of times when you are writing programs and compiling them, in order to save speed, the software may not retain the, or I should say the compiler may not retain the symbol names for your internal functions. So any of the functions that you only used internally, those function names might actually get stripped away. That's a common way to save space and shrink down the size of the program. When this happens, what Yara Pro attempts to do is it still identifies that a function is there, and that's what you see here is all these sub underscore some number. It just gives it a brand new name. But each one of these that's listed right here is a function that does something. And I'm looking underneath the functions tab right now, which is actually a lot easier way to navigate it than I was doing before. I'm just a little bit more familiar with another interface. So if I double click on any of these, I can go and look at the functions, and some of them are tiny and don't do much. Others, let's see if I can find one. Others, like this one, looks like it does a whole bunch, and it shows you a zoomed out view of the graph. So you can kind of look here, and you can look through it. One of the things that I can notice right off the bat is that this thing appears to be loading that alphabet. The one that I pointed out earlier appears to be the base 64 alphabet. I can actually jump to it and look at it. One of the nice things about Yara Pro is that it does provide this feature that allows you to double click on things to pivot between them. So what I've been doing is when I jump between pieces, I double click on the variable name. In some cases though, like in this particular one, this variable is used in multiple places in the file. Or maybe this one isn't, but for whatever reason in this window, when I'm being shown the variables, I can't double click to get back, but I can hit X, or I can right click on it. Come on. Sorry. Sorry. So I'll go back here. I can right click on this, and I can pick the jump to cross reference or xref of the operand, or to the operand. And that is basically saying that all of these things are strings, which means that they're, const char start something or other, var1 equals some string. They're all some sort of construct like this, right? Right? There's something like that, which means that there is some point in the code where I do something like n equals sterling name, right? Or whatever function I happen to pass that to. So when I'm looking up here, this is giving me a view into all of these things, all the variable declarations and everything. And then when I hit X on it, or when I do the jump to xref to operand, which they show you the shortcut over here, so it becomes very easy to learn what the shortcuts are by right-clicking on stuff. Then that gives me a table that tells me all the spots where it happens to be referenced or used. So in this case, it's only used in one spot, which is nice. It happened to be that one function that I was looking at. So another thing that's very helpful in here is when I say, hey, this is interesting, I can actually go here and I can say, like this looks like a 64 decoder, and then put like my initials or something there. So I can add something like that. Now I've got a note right here that I can actually, I'm not editing the program. What I'm doing is I'm editing the project, the program, and being able to put notes in here. So I'm able to leave little tips to myself because an analysis job like this, depending on how deep I want to go and how much information I want to gather out of it, could take days or weeks even. And if it takes days or weeks, I don't necessarily want to be stuck having to dive into, my text editor, or OneNote, or my personal MediaWiki instance, or Jupyter Notebook, or something like that. I don't want to have to dance around those things all the time. This allows me to put some notes in here right next to the different code that I find interesting. The other thing that's nice is I can go in here, and if I think I've found a better name, or if I think I've found the purpose of a particular element, what I can do is I can actually rename. So I can store a new variable name for that variable that's going to be global within my project file. So again, I'm not editing the program, but what I am doing is I'm coming up with a more descriptive name after I've analyzed this function to name this alphabet. So I'll call it base 64, like base 64 alpha. I'll just say alphabet, right? So I'll do that. I hope it's within the 15 character limit. And then I can do that. And now I can save it again. And this means that when I load up this program later, and I'm trying to look for this code, I can more easily find it because it changes it over here, I think. I might have to, or it may not, but I think I can search for it somewhere around here. Yeah, search. So I can search for so I can search for base 64 alphabet, and I can keep searching if I want. So I can keep, so maybe I won't find it, I don't know. But it'll search the entire system. So it allows me to come back and search for those things. I'm going to jump back here to the out of view and search for the text again. I'm just going to go all the way back up to the top of the program. So go over here. The other thing too is it ends up storing it over here too, if I remember correctly. So I can pick out the strings list over here. This should look familiar to all of you. Yeah, see, it goes and retains it. So this should also look familiar to all of you because this is basically the same strings list that I was showing you earlier when we ran when we were going through this stuff. So what you're seeing here, more or less, this one. I don't remember which version of the file I have open on the other window, but you can see these A's followed by this value. That alphabet that we were just looking at is here. That RSP120 that's at the top, well, it was up here somewhere. Is there, this YYYYYXYYYY, it's still here. And then the X, the inverse of that as well, still there. So the next thing it can do, if I want to, is I can try and look at these ones. So I'm going to try and look at this. And this one's actually appears to be referenced in a couple of spots. So ends up trying to copy it to do something with it. So it runs it through a copy operation. It runs both of them through some sort of string copy to put them in another location, right? It's basically it trying to find or trying to copy the data out of memory for some reason. The other thing I can look for, which may be more informative to figuring out what's going on, what's the purpose of this, is actually to look at those other two occurrences that I saw. So I'm going to go and look at these ones right here. And this one happens once in the program, and it actually happens right here. And this illustrates another really useful feature of Yara Pro. Again, right here it tells us which function we're looking at. So each one of these graphs is actually representing a function that you would have defined as like a subroutine in C. So we're looking at every single one of the decisions within that function. You can also scroll up to the top of it, and not only can you see the function, you can also see in some cases, again, this is where Yara Pro is able to figure it out, and sometimes it can't figure it out because it's not obvious. But in this case it did. It figured out what 4 variables are supposed to be passed to this function. So this function takes 4 character pointers, or character constants basically. Or string constants, I mean. This is the use of that string that we were looking at. And what it ends up doing is it loads memory from somewhere. So it loads an address into EBX. And then what it does is it falls into this code, and then this makes a decision using the string function. So this is a common function that's available on Unix systems as well as Windows systems, and this is a really good example we were saying earlier where a lot of the methods that we'll look through here actually translate between the two different platforms, or pretty much platform agnostic. So I can actually look up, this is always a good habit, I can actually look up string or stir, and what this basically is locates a substring. So if I give it a string, like like my name or something, Coleman Kane, and then I have it search for the substring man, I would point Coleman Kane here. I put a pointer to Coleman Kane here, and then put a pointer to another string, which is just the 3-letter string man here. So what this is doing is it's actually looking for, as the second argument, it's looking for this string in whatever this argument was that was passed to it. So it says argument offset 4, which you can see up here is going to be labeled right here. So another feature of Yara Pro that I'm demonstrating here is that whenever you select a variable in a function, it actually attempts to highlight every single copy of that variable, or every single reference to that variable throughout the entire function, so that you can use that information to help follow like data flow throughout the code. So that's, at the end of the day, like for a lot of this stuff, that tends to be what you're working with on most computers, is a data flow problem. So the other thing that is a feature that's provided here is that whenever this happens to have a jump call that goes back to an earlier point in the code. So if you think of all the different pieces of your function as being graphs, if you can show that there's a cycle in the graph, there's like a mathematical way of actually showing that. They run that analysis on every single one of these paths, and if any of them ever shows a cycle, what it does is it actually highlights that branch using a bold line. I would recommend that that's when you're analyzing software and trying to figure out what it does, that's very indicative of any sort of looping algorithm, or most of the common like data manipulation operations that you're going to deal with. So when I go through here, I can actually look at the graph that's right here. I can expand this so it's bigger, and I can see there's 1, 2, and that looks like it. Maybe a third one over here, so maybe 3 cycles in this graph where it's trying to do some sort of repetitive work, where it's basically looping until it runs into a terminal condition. Those end up being nice places to go and look for possibly unique code that was implemented by the author or something like that. So I found that one of the big things to help me determine what's going on in a function is to look for those looping sections of code, because a lot of times that's where the data manipulation algorithm exists. So in this case, what this ends up doing, and I already did some analysis, so I kind of have some foresight on this one, but kind of walk you through it. What it does is it gets a reference to this marker string that it's looking for, and then it tries to find it in the string that it was provided. If it finds it, then it ends up taking this path here, and if it doesn't find it, then it ends up incrementing. So it ends up moving to the next byte in the pointer, and it actually modifies argument 4 in place. So it modifies the string pointer that it was provided, or the local variable created to store that string pointer. And it basically keeps walking across that until it compares these two, and basically if they end up being 0, if they end up both being 0, then or if they end up both being give me a second, what's going on here? Yeah, if they end up both being or I should say, if this string is found as one of the substrings in the input text, then it stops this loop and it proceeds forward to go and do something with the data. So in this case, it follows this path to go and do the something with the data, and what it ends up doing with the data is it actually calls the string copy operation. One of the interesting things about this, or one of the other key observations about this, is that if you look at each one of these things, if you find that thing in memory, that is 5 x's followed by a y followed by 5 more x's. So that's 5 plus 1 plus 5. So that's 11 bytes long. In all of the cases where we saw this artifact used to identify a URL, that ended up being right here. That's 11 bytes. So if you find the beginning of this, then what you know is that the beginning of this plus 11 is actually the H in HTTP, or the beginning of your URL. So what I can do is, if I go back here, what happens is we get through this little routine right here, and then we end up with this EAX actually having a pointer, or containing the pointer to the first byte or the first X in that string. We add 11, which is 0B hex, or if I want to, another feature that I can do is I can actually convert this to different numerical representations. So if I want, I can represent individual numbers as hexadecimal or as decimal, like I just did, so that shows 11, or as octal or as binary. So whichever one happens to be more useful for my particular situation. So then if I scroll down, I end up seeing roughly the same, or a very similar operation happening again, but it's using a different string. It's using the ones that's y's surrounding an x. And then it jumps down and it basically does the same thing here, which is it moves the pointer 11 bytes over after it finds the beginning of the string, so that it can get the beginning of the URL. and then it can copy that into a buffer that I presume it's going to use to try and do some other operation. So then, this is 403.300, I think. Let me double check. So I'm going to make a note here that says, I think I have it down here though. It just does that. The other thing I can do is then I can also use that X again to find out where is this called from. So it's called from here, which is another big function that's doing some random stuff. So and another function that was only found within the program is here. This one's interesting because it looks like it's trying to open up an exe file, or maybe it's trying to open up an exe file that it wants to read. So it's trying to do a number of things, but one of the things that it's trying to do is find or is call that function that we were just looking at, which is the calls right here. So, and I know that because I just wrote it down in my notes. So I refer to my notes, and then I can go and find where I was before, because this does get to be a little bit of a mess. But I can navigate in and out of the the different functions that way, and I can find out what's referencing what. So I can build the connections between them, even if I'm not like literally looking at the entire map of the thing on the screen. So the next thing I'm going to do is I'm going to say, okay, well, I'll use the technique that we had with objdump before to go and analyze the code in here, because this is kind of a curious little routine. Maybe there's some there's some value in it. So I think that was it. So this right here, again, uses, nicely enough, the addresses that are the same numerical address space as Yara Pro used as well. So one of the nice things about a lot of these tools that do the analysis for you is they actually give you the addresses of all the code and all the data in terms of where it would be if the program was loaded in memory. So I can use a search for that function, for that address, to try and look for the beginning of the code that I was analyzing before over here. I will say that if you want to, you don't have to jump to another program. You can also go in here and I believe, you can put in like 10 here, and then every single one of these things, it ends up showing you the opcode bytes. I just end up finding it a lot easier for me to be able to go through this using objdump. I just find it to be a lot more readable when I'm trying to analyze the data that's located in the program. As you can see, this ends up being broken up across multiple blocks, and on top of that, I do happen to be running this in a Windows emulator, which is going to maybe present some issues with like copy paste and everything. So, but the address is 403.352 is my location, so 403.352. This gives me the beginning of that loop that it's running right here. So what I'm going to do is I'm actually going to put together another rule. So remember I was putting this one together. So what I'm going to also do is I'll just make I'm just going to skip all that stuff, sorry. You'll notice I have a handful of habits. So what I'm going to end up doing is I'm going to extract those bytes, and I'm going to basically go through and grab these all the way down. So again, I was searching for it in objdump, and it highlights both things. So I've got about a handful of lines to get. So I'll just try and get these as quickly as possible. what I'm basically doing is I'm trying to copy the binary data here. As you can probably imagine, there is a ability for you to write small programs, Python or something like that, that can actually extract this stuff manually. All right, not manually, I'm extracting it manually. Can extract this stuff automatically. If you were to give it a range or something, I don't happen to be using that right now, but I could very easily write something that does that. This only took me maybe about 45 seconds or something to do by hand. So there's one of them. And then if you remember, we saw two of them, so I'll call the other one YX loop. And it's actually down at, I memorized where it was, but I also wrote it down. It actually starts right here. So it's this one to here. So apologies for the tedium here really quick while I do this, but it is a helpful exercise to see this stuff built out.
Is it opcode byte you are trying to copy?
What's up?
Is it opcode byte?
Yep. Yeah. So the reason I'm doing this is because just like we put together a Yara rule to look for files that had certain strings that were like, you know, human readable bytes, which is what you have up here. You can also apply the same concept, same logic to the data bytes that are encoded in there. When we were looking through the x86 assembly code a week ago, we were able to see some of the opcodes, and if you went to any of the sites that I had talked about in the earlier lecture, the one that I had on what was it, Thursday before last week, or if you did any research like x86asm.net or something, they actually go and allow you to look up various operations by the data bytes. Each one of these data bytes, so like the 68 for instance, is actually associated with a particular instruction, which means that if you wanted to run that instruction any time on a x86 CPU, you're going to need to use that byte. So one thing that you'll notice after I've copied all these is that I went to these two sections in the program. So I went to this loop here, and then I also, which is the one that's dealing with the string with the, yeah, so this one's the x's surrounding the y, and the other one is the y's surrounding the x. I pulled both of these two out, you know, with the byte extraction, and then I put them into a Yara rule right here. So now, I can look for this Yara rule in, where did I put it? Sorry. It's apt1_ex, so actually I'll just do this, rex1.yar, and then I'll look at it. So the R that I'm putting in here says to look at all the files in that directory. So now what you'll see is that I actually have all three of those samples that hit on this one are also hitting on this one. And I can actually dive deeper and just erase these for now and see the exact data is actually hitting on it. So XY loop, YX loop. So it actually hits on all of them. one of the things too that you'll remember is that this code, so this loop is actually referencing the offset of this string right here. So it's referencing the pointer of this directly. So if I go here, I see that that is 4055 DC, right? And then I'll jump back to the code. You can see it right here is 4055 DC. So of course it's like oriented backwards because on this is another characteristic that you'll notice is common in Intel. It's not a rule that's hard and fast across all CPUs. Some CPUs store it the other way. Intel stores it this way because if you read if you think about reading a number off of a page or doing addition or multiplication or something like that, usually work on the least significant digits of the number first. And then you work your way up and you build your carry all the way up. CPU's got to use the same algorithm to do math. Makes sense that that in the lower numbered addresses, it stores the least or the lower significant bytes of data for any numeric data, so that it can easily replicate that same mathematical algorithm. So that's here. I'm going to go back to my patterns. What I can see here is that all the bytes in this are the same. So all these bytes are identical except for, and really except for this one. But our analysis indicated that these 4 bytes here are actually the address, so the absolute address of that string in memory, which means that if I was to happen to move that string somewhere else in memory, like I did when I used the algorithm again here, which they probably just copy-pasted the code and then changed the variable name, then it changes the address. So I already know that. What Yara allows me to do is actually put patterns in like that after I've made an observation like that. So now I've changed it and I've shrunk it down to one less pattern that I need to match on. I've also expanded the net to not just be looking for those 2 variants, but any permutation where those 4 bytes are different. So I don't know what this is going to turn up, but you can try seeing. I'm going to hide this. So it still just shows those particular examples right here. But you can see that now I match on both of these things. So I've gotten a broader signature that, say in the future, if I end up having more samples of this malware where maybe they've moved the code around or something like that, they've changed those addresses, then that code will change. Also, if you remember, when we were looking through this, one of the other interesting characteristics was that the timestamps of all 3 of these samples were the same, which kind of led us to conclude that they were probably built at the same time, and then the data was modified with like a hex editor or something after the fact. So then I might put, say, this example of code into my report as well. I'm not going to do that right here, just in the interest of time, but I also documented a, why is it like this? And then I kind of gave a very brief pseudocode version of the algorithm that's happening. The other thing that I found in there was this, which is a base 64 string. So let's go look at that. That one is actually right here, right? So we were looking at that earlier. So it ends up being this code right here. So there's this loop that goes through, and it's supposed to be doing some sort of decode or encode of base 64 data. I'm not entirely certain exactly what it's doing, but it is like a bunch of code. So what I might do is I might basically jump in here and do the, do the same thing. So that, I think I have it over here, actually, yeah. So, 401BFF. So this ends up getting me to the beginning of the code that's right here. And I can run the same type of, the same type of analysis if I wanted to. This is a really big function, so I'm not going to jump through and make a whole signature for the entire thing. One thing I will do though is I can go and grab this, and there's a, if I want to, there's a shorthand way to do this as well. So. Go through, grab these things. And then like that. So what I did was a sequence of, I grabbed it. One of the nice things about Vim is it allows me to grab rectangles within the text and cut that out, and it'll just smash the text up. So I can do a horizontal and vertical elimination. And then what I did was I did a find replace to replace all the new lines with spaces, and then I replaced all the spaces that were 2 or more spaces long with a single space. So then, whoops. I can do this, we'll just call this setup because it looks like it was just getting into the beginning of that loop. So then what I can do, I'm going to take away the S so I can see. So now you're seeing that I wrote signature that's just based on that, where I just really grabbed all those bytes, and it actually happens to match on a whole bunch of more samples that even that original rule didn't. So a bunch of those samples have a bunch of code that's possibly, that they possibly share in common with that one piece of malware that I saw. And so it gives me some more pivots to kind of work off of. So for instance, I might load up this one here and see what the strings look like in it. So you can see another one of these base 64 strings is here. However, the other strings that are in here are actually ones that we didn't see in this version of the software or anything else, and they happen to do other things. So just kind of one piece of insight here that I know from working with this is that built a lot of really small backdoors to do little tiny functional things. They kept a lot of common utility code that would be shared among them, among these different things. So they had a C file that had like a base 64 decode encode function, and they copy paste that into any program that they're working on that they want to. And so that's kind of one of the artifacts that you're seeing here, is that when you do those binary level analysis, you can start to find other programs that share functionality because they wanted to achieve a certain outcome, regardless, or share some functionality or share some common code without being identical or without having some of the core features in there. So what I like to try and describe this as is almost like feature extraction, where you're analyzing the code to try and find code that accomplishes certain tasks. So maybe something that's like a wrench in their toolbox or something like that. And then you start to identify which of the programs that they have actually implements some of that code. So this is a really great example of that, of where they wrote a different backdoor that actually does different things, but they end up reusing the same base64 code. And so working through these things and trying to find, say, new features that are added and everything is one of the big things that you'll use this type of analysis for. So so that ends up being, looking at this. And the other nice thing too about it, and one of the reasons why I didn't just rely upon this string, hypothetically, if I wanted to, I could replace the letters in this string. I could shuffle them around, or I could permute them any way I wanted, as long as the thing that's building my base64 data is using the same alphabet that whatever backdoor that I want to read it is using. So me extracting the algorithm that I pulled the disassembly for, and then writing a pattern around that, gives me the capability of writing a signature that's going to match on code doing the work, regardless of what alphabet they choose. And as you can see, there's, I don't want to do the math in my head right now, but there's a lot of permutations of this alphabet that you could use. And as long as you're making sure that the input and the output, or I should say the controller and the backdoor, so the remote side and then the compromise side, are consistent, using consistent alphabet, you don't have to change the code at all. But to like a naive analyst who will just may just grab the alphabet or something like that, that ends up being the case. Or that ends up being basically a better signature, a more survivable signature is what I call it. Ditto for these. So there's nothing that says that they can't have a string with a B surrounded by all A's, or a 9 surrounded by all 1s, or something like that. The only reason they don't is because they haven't chosen to do that yet. Or maybe they did choose to do it at one point, and they have since moved to this. I don't know. By pulling the code signatures that we have right here, so by pulling this XY loop thing, there's actually no code in here that's testing whether something is an X or a Y. It's just testing, it's a certain loop that's doing this weird string comparison thing. One more thing that I'll just kind of point out that is a, I can't remember, yeah, it's like 403,300, right? So I'll jump back to that, 403,300, right? So another thing that some of you might pick out is that the way this is working is this might be somewhat naive. I'd have to go in here to really get a good feel for it, but generally speaking, you could actually use another function. For instance, in Linux, there's a function that's called mem that actually allows you to give a buffer size for the haystack and a buffer size for the needle. So if I wanted to, if I was going to really do a small version of that, I could really call this function and give it haystack could be the entire program memory, and then needle would be what I'm looking for, right? They didn't choose to do that in this case for whatever reason, maybe based upon their constraints and wanting to only be wanting to make sure that it's compatible with certain versions of Windows or certain libraries, or the tools that were available in their version of Visual Studio or something limited them in this regard. They're doing this loop around the string operation, and then they'll just kind of like iterating it 1 byte forward every single loop. So that might actually be a naive way to do it, and that might evidence some information to you about the sophistication level of the developer, and that itself might yield a significant pattern to look for, because, like, there's more than one way to accomplish any problem. Someone tries to accomplish it one way and it works for them, they're going to reuse that method every time, either by copy paste or by re-implementing it. So this is kind of what you're looking for there as well, in addition to just code to get the thing done, the knowledge that there are multiple ways to, accomplish something. If you find some author is accomplishing it one way, it's very likely that they're going to use the same way to accomplish it again. So then another example that I'll go at is this one, and I'm going to shrink this Vim window up so you can get a better view of this. So I found this string as well, which I thought was really interesting. It's right here. So this one is what, if any of you have been programming in C or C++ for a long time, have used printf. I'm trying to remember which other languages also it's available in. You may be familiar with that. You can basically put together formatted strings using these percent fields or percent placeholders, and then certain characters after them. So they'll look for alphabet, numeric, and I think the period as well is an acceptable identifier. But if you happen to have access to a Linux system like Remnix, you can also do, I think, this, and it goes and explains to you the format of the format string. So this actually goes into explain to you all the different possibilities there are for that, how it works. So I recommend using man to go and read that stuff. There's also a lot of documentation on the internet about it, which is perfectly fine too. The reason I'm pointing it out, is because this means that whenever they display this, they seem to want to put a whole bunch of information in here. So I can find out what information they're trying to put in there by looking for that string. Again, it has some sort of functionality, or else it would likely not be in here if it didn't have some sort of purpose. You can find it in the code, and then I could jump to where it's being used. And then what I find is that it's calling sprintf, and it's putting this sz agent followed by that string. So if I want to recreate what's happening, I'll do it on my notebook here. I can do this, right? Sprintf, sz agent, this, and then goes in here, and it says name, some data value, it's right here, which gets filled at runtime somehow. So I'll put name, so name, unknown, I'll just put unknown in there, and then it's got, I'm just going to kind of work up, because that's how this ends up getting built, is that the last argument in the function call is up here on this one, and then the first argument is right here. So then it ends up being year, month, day, hour, minute, second, and even milliseconds. And the important thing to keep in mind is that what it's doing, again, this is a good example of kind of the limitations of the architecture, is that it wants to build the function call as basically a bunch of parameters on the stack. So it pushes them on the stack. In order to get a value from memory somewhere onto the stack, you end up needing to bring it into the processor first, so into the EAX or the RAX register, depending on what architecture you're using. And then you want to push it onto the stack. And so that's what's going on here. And then this one, I guess, was able to actually do a direct access for some reason. So for whatever reason, that's how it was compiled. So it pushes milliseconds, then this actually gets moved to EAX, and then it's pushed, so it's seconds, milliseconds. So we can walk through, we can walk through this thing and see that this was going to be a year, month, day, hours, minutes, seconds, milliseconds, I guess. So for whatever reason, it's getting all that stuff, maybe to get a timestamp to find out, say, what times the program's run or something, or how long it's been running or something like that. The next thing would be to figure out what the purpose of each one of these things is, which I can go, and again, on any one of these labels, I can go and push X, and it actually gives me a window of what's going on with each of these. So the one I'm looking at is right here. So it's this plus 177, so it's actually this one. This is the one I'm already looking at, so there's 3 other ones. So for instance, I might go all the way up to this one and see that it's calling sprintf on this thing right here. So it calls this function after passing that as an argument to it. So I might want to go into that function to figure out what that function does with the name argument. And this actually ends up being like WSA data. It ends up being the WSA, so it's calling WSA startup, and then it's get host name. So, you know, kind of short jump here. If I go and look at the WSA startup function, which is a Windows program, that's the function that tells your program to set up the memory space to start dealing with Windows sockets, which is how Windows sets up TCP/IP. Then after that, you can actually call all the functions that have to deal with TCP/IP data or the TCP/IP subsystem within Windows. One of those functions is this get host by name. Now, what the get host by name does is if you give it a buffer, it finds out what the current host name is and stores it in that buffer and then gives it to you. So what's happening is this function is called so that the program that's executing can actually get the host name that a system thinks that it is. So in Windows, this would be your computer name, right? So we've just walked through to find out what this argument is. And that argument, again, is the first argument in this little structure here. So what this ends up doing, and I'll go back out to the documentation here, what this ends up doing is this is the timestamp right here, right? And then this ends up being the host name or the computer name. And one of the beneficial reasons for them harvesting a computer name like this or host name from there is that there's a lot you can learn from what people name their hosts. So for instance, if you work at some companies, many times they might actually include the company name in the host name, or a person who's an important person of some sort, or honestly any person frequently will use their own personal name for their computer, because that's the dialog boxes that you get presented with when you boot up your computer for the first time to try and have you set it up that way. So bad guys, if they've sent this backdoor out to a whole bunch of different systems, they can now have those systems check in and give the bad guys a list of when they checked in, so what times they checked in, and also what the system name was. In this case, this right here tells system name, which then can allow the bad guys who may have blasted this out to like 1,000 different people, enable them to narrow down to the 2 or 3 interesting people on that list. So that's a reason why they're doing this, and looking through the code like we're doing the analysis, and also doing the binary level analysis, the instruction analysis to figure out what the functionality is. but also doing the data flow analysis, so trying to follow these data values around to see what they're used for, what they get filled with. So I can look at this one too, and I'll do the same deal, right? So this is right here. This is the 172 offset. So we'll go up here and see where it's used, and it's also filled as the second argument. So my guess is that after get host by name, we're going to want to find out what arg4 is. So I'm going to highlight it. And then I'll go down here and I'll try and see what arg4 is. And it looks like what happened is it called inet n2a, which is the network 2 address, or the numeric 2 address. So it's to give or numeric to string. So it's to give a string representation of what the IP address is or whatever. And then it copies that into this buffer that I gave it, so that I have that. So maybe I'm getting the not just the host name, but also the IP address that the machine thinks it is. And that might be useful, for instance, if I have sent something like this out to a company and or to, say, an organization, and I know that I've compromised one of their systems, but there's also 3 more systems that for whatever reason I don't have access to, other than that I can see them checking in, so I don't have any way to actually control them. I might be able to access them internally if I can reference that. So the other thing too, it happens to be carving out some other information, which is getting information about the user profile, likely the username or something, because even if somebody names their computer and gives it the username, they may not necessarily, or I should say, if they don't give their username or their personal information in the host name, very frequently they will give it in the username that they choose for themselves. So that's what it'll pull here. So all that information will get bundled up in some manner and get delivered over to the other system when they're checking in. So, yep, that ended up doing a kind of, there's a lot of other paths you can take with it. I went through these 3 paths because it kind of gives you, a handful. This was a more general algorithm I saw used in a lot of samples, so gave you the ability to see what happens if you kind of go and analyze through and look for code that might be more general purpose. You can build detection around that might help you find other malware samples that aren't just exactly the ones you were looking for before. And then finally, this is doing the code level analysis and data flow analysis to try and find out what comprises, or I should say what functions are occurring.